Okay, then let's continue. And after this introduction to F-statistics, now let us look at the F-statistics proper. So before we start, maybe a brief review of what we've seen in the last hour, because it was quite a lot. So we are interested in a model for some data y Rn, and we now looked at comparing two models which form subparts of this full model. One is the full model itself, which we also wrote as x1, x2, and beta as beta 1, beta 2, where this whole thing is n times p, and x1 is n times p1, and x2 is n times p2, and appropriately the same, accordingly here. So this is p-dimensional, beta 1 is p1 dimensional, and beta 2 is p2 dimensional. And what we also defined are these errors under each model, where E12 was y minus x beta, without the brackets, and E1 was y minus x1 beta 1, and what I forgot here was the hat, because this was upon estimation. So this is of course the same as this. So now the F statistic is defined in terms of these errors here, these residual errors, and it takes the F statistic takes the following form. So F takes in actually these residual errors, which must be larger, or if there's essentially, if the model fit is perfect, must be larger or equal to 0. So it takes in E12 and E1 and maps this onto also something positive, and this looks as follows. So it takes in E1 and E12 and maps this onto the value. Like always, I'm just writing this as a function because then one knows what the f value depends on, and this is defined as, so fe1 E12 is defined as Et1 E1 minus E12 T E12 divided by P2, and the whole thing divided by E12 T E12 divided by n minus p. So this is, it's a fraction, and in the numerator, maybe that looks a little bit weird now. In the numerator you have a fraction, and in the denominator you also have a fraction. So that's what the F statistic looks like. And now the question is, what does it mean? What does it want to tell us? So the first thing Yeah, okay, so we realize a couple, or we recognize, not realize, we recognize a couple of things here. So let's look at that in more detail. So first of all, we recognize this, maybe without the P2, we recognize this because we just talked about it. Yeah? So that was motivated from the idea of comparing two models, doing a log likelihood difference, which is the same as a likelihood ratio, and corresponds to comparing the full and the restricted model. So the F statistic has this idea of a model comparison between a full and a reduced model, so between the full model here and the reduced model, which I didn't write up again, but you see parts of it here. It implements this in this numerator. Then in the denominator we have this expression. So does anyone remember what that is? Roughly? No? Okay, so this, if you write it out, you get y minus x beta hat t y minus x beta divided by n minus p. So have you seen this before? Sigma square hat, exactly. So this is the variance estimator. Yeah. So this is the same thing that we used. This is for variance estimation. It's just now with this E, it's written a little bit shorter, but it is the estimation of the variance, of course, under the full model. Yeah. So what this means is that whatever the F statistic does is expressed in terms of the residual variance of the full model and the full model is, of course, I'm just writing it up again, is of this form. Yeah. Good. Then the remaining thing to talk about is, of course, the numerator, and as I previously told you, this is embeds a likelihood ratio comparison, model comparison, but of course one can also express that differently. So here we have this E1 T E1. That's the residual sum of squares under the reduced model, and from this is subtracted the residual sum of squares under the full model. So this difference here is a reduction of residual variance per additional regressor, and I explain that more in a second. So to understand this from this reduction of residual variance, it's easiest to consider essentially the case where, or to consider the case where the full model is the true model and where the reduced model is the true model. Yeah. So let's first assume that the reduced model is the true model. Yeah. So if the true model is the reduced model, then the additional regressors that are in X2 and which have their associated beta parameter beta2, of course, don't explain anything interesting in the data, because the only thing that determines the data is what's happening in X1 and beta 1. So if the true model is in fact the reduced model, then beta hat for beta 2 will be approximately 0. Yeah. So because you can view the reduced model always like this, so x1, x2, beta 1 and 0, so a p2 dimensional 0 vector here, that is the same thing as x1 beta 1, yeah, because if beta 2 is 0, this doesn't have a contribution. Now this means that the addition of these regressors in X2 doesn't do much. So if the true model is the reduced model, what we actually have is that E1t is approximately the same as E12t E12. Yeah. So if the true model is the reduced model, then we learn that we essentially get a relatively small numerator, or expressed in this language, the reduction of the residual variance per additional regressor is low. Yeah. Now, if the true model is the full model, which by which I mean that the true but unknown beta 2 is not 0, so then this is essential. Then of course the estimation for beta 2 is also not 0, so let's call that larger than 0. And in this case, it's there is stuff in the data that can be explained by these beta 2 regressors in the design matrix, so the stuff that is in the part X2. So the variance under the reduced model, the residual variance might be quite large, because there is something in the data that is explained by this X2 beta 2 contribution. So epsilon, E1 TE1 will have a certain value. Now, if one looks at E1 E12. This, of course, can capture all the variance. So it's relatively low. So E1 TE1 will be larger than E12 E12. So in this case, we get in the numerator quite a large value, which is due to the fact that this value is large here. So this value is large and this value is relatively small. So we get a high F value if the regressors that are here, if they contribute significantly, I don't want to say significantly, but if they contribute significantly to the explanation of the data. And the whole thing is expressed per additional regressor. Yeah? So it's normalized by P2. So it's a kind of, the numerator is a standardized measure of how much reduction of residual variance is afforded by these regressors in part X2, and it's normalized per regressor. Yeah, so it's not, so if you have, so because you would assume that if the true model is the full model and you have many regressors, then you would have quite a big reduction, but then you want to know, is this really, so how does each regressor in X2 actually contribute that? So you normalize this by P2. Yeah. So this is a way to understand the F statistics. So motivated from likelihood ratio tests, one comes to this formula and this expression, and then one can interpret also from a reduction of the residual variance, of course always normalized with respect to the overall variance. Yeah, so if the reduction, so this means in terms of this normalization, or in terms of this normalization, this means that if the reduction, so that the absolute value of reduction of residual variance is not that interesting. For example, if it's 10, if the overall variance is also 10, then that's not that interesting. But if the reduction in the residual variance is quite large compared to the overall variance, then you get a larger value. Yeah. That's F statistics. It's a little bit more complex than for T statistics, but then it also does a little bit more in terms of model comparison. Questions about this? No. Good. So then I next cover briefly the distribution theory for F values. Well, this will be fairly brief, because that's actually more demanding. So what we've seen so far, that was, if you think back about the t-value had some meaning in terms of the ratio between an effect and the variance of this effect. And that's, you can do without any hypothesis testing. Here you can see an F value as this contribution to explaining the data afforded by the regressors in X2. Again, you can do that without doing any hypothesis tests and without looking at any p-values. So F values, which of course are also sometimes visualized on brain maps, are meaningful regardless of whether you do hypothesis tests or not. But of course, you can also do hypothesis testing with F values. And this is commonly done using the F distribution. And here, because the distribution theory for the F values is actually more demanding than to basically mathematically motivate, then for the T statistic, I will just sketch what's going on. So first thing is, again, like for the T distribution, what is the F distribution? The F distribution is the distribution of a random variable, let's call that x, which is defined again as a ratio of two random variables, namely y1 and y2, which is now not the data or anything, but specific random variables, namely y1 is a chi-squared distributed random variable with m degrees of freedom, and y2 is a chi-squared distributed random variable with m degrees of freedom. Again, the F distribution has a density function, which one can express as a function of these two values for degrees of freedom, so m and n, and so this is now the density. And again, this density looks a little bit funky, so it involves again the gamma function, and has this, oops, not F, gamma, has this normalizing component. So this is again a density function that you don't have to memorize. You only need to memorize the normal density function, but I'm just writing it down so that you know that it's there. So the dependency on x comes in here, minus 2 divided by 2 and divided by mx plus n m plus n divided by 2. So this is the density function, which depends, and this is the important thing, depends on both m and n. And it's visualized in figure 2.1. So this actually looks, it's a little bit like the chi-squared distribution. It looks always a little bit different depending on the parameters. Well, that's a common thing for all probability density functions. So it's visualized there. You can look at it. The most common thing for a little bit of larger degrees of freedom is that it takes kind of this shape, roughly. Yeah, and here we have 0, and here we have the density. Now that's the F distribution. Why is this chi-square distribution thing here interesting? Well, in the F statistic, both the numerator and the denominator are derived from residual sum of squares, so residual error sum of squares. And again, for these error sum of squares, it doesn't make any sense for them to be normally distributed, because they cannot be smaller than 0, right? So because this is always sum of squares, so if you have negative deviation, they get squared, and so you get something positive. So the F statistic, the components of the F statistic it makes sense that they are chi-square distributed, but again, it's not as easy as one would like to have it. So what is actually chi-square distributed in terms of the F statistic are the following quantities. So if the null hypothesis is true, that is F beta 2 is 0, then epsilon 1 t epsilon 1 minus epsilon t 1 2 epsilon t 1 2 divided by sigma square is chi-square distributed. And this actually this morning when I prepared for the today, this is not easy to see. So I have quite I find this quite surprising, but this is what I find in the literature. So at this point, I have no other way to believe that. If you have a proof for that on your mind, let me know. But you can also, otherwise, you just also have to believe me. I find this a little bit surprising because in principle, this would first think that these are then the same, so it all goes pretty much towards 0. Well, it's yeah. So it makes it must be something like this, so that there's a high probability close to 0 for this term to be distributed according to. The other thing that I have less of a problem of accepting is that ET12 E12 divided by sigma square is also chi-square distributed with degrees n, degrees of freedom n minus p, because we've seen that before, because we talked about the distribution of the variance estimate, and the variance estimate, and there we learned that the variance estimate or a normalized version of it is distributed chi-square, and there we actually looked at the variance estimate, so something like this, divided by n minus p. Confusing. The variance estimate, which is E12 t E12 divided by n minus p. So that's the variance estimate. We learned that a normalized version of that, namely multiplied by n minus p and divided by sigma square, is chi-square distributed. And now, of course, this thing here is just this. So we've seen essentially the chi-square distribution of epsilon t12 and epsilon 1 epsilon. Jesus, I always said epsilon e12 t and e12. We've seen the chi-square distribution of that before. Yeah. So this is fairly hand wavy, but now really deriving these distributions would require considerable effort that we don't want to spend. If we accept that these quantities are chi-square distributed, then it's fairly easy to accept that our F statistic is distributed according to the F distribution, because the F distribution is defined as the ratio of two chi-squared random variables divided by their degrees of freedom. Now, if we divide this by its degrees of freedom, we get divided by P2 sigma square, and if we divide this by E12 T E12 2 divided by its degrees of freedom, n minus, there's a p2 missing. Well, let me check. Should be, let's go back to where we are. Oh no, n minus p, sorry. N minus p, sigma square. And then we are back at our F statistics. Yeah? So we have now divided these chi-squared random variables by their degrees of freedom, and then we divide both of them, so one by the other, to get our F statistics. So we are back to our F statistics, and we have now seen in a fairly hand-wavy fashion that the F statistic is distributed according to an F distribution. Yeah? Because the F distribution is defined as the ratio of a chi-squared random variable and another chi-squared random variable, both divided by the degrees of freedom. So that was a very cheap introduction to the distribution theory of the F statistic. You can, if you are really interested in that, you can look into mathematical statistics book and try to trace how from the normal distribution of the data and then the normal distribution of the prediction error or the residual error, and you get to a chi-square distribution. And if you then put together multiple of these chi-square distributions in an F statistic, how this then leads you to the F distribution, if you're really into it. Good, so that's briefly the distribution theory, and again, of course, this distribution theory can be used. So now that you know what the distribution of the F statistic is under a null hypothesis, namely under the null hypothesis that the beta 2 are 0, then you can use these densities, and if you have a large F value, for example here F, you can look at the probability of this or more extreme value to occur, which you would call a p-value, and if this value is relatively low, you would say, okay, the null hypothesis that the beta 2 parameters are 0 is not true, and in terms of model comparison and relating this to likelihood ratio tests, you would then say the null hypothesis that the reduced model is true can be rejected because the probability that under the null hypothesis to observe such data is small. Yeah. So now let's look at a visualization of that, because I think that makes things then maybe even a little bit more intuitive. Yeah, sorry.
So if we construct null hypothesis the opposite way,
that beta 1 is 0. We don't do that. No, so this is again the F. So what you could do in this regard is to reorder the regressors. So basically, if everything is nicely orthogonal in your design matrix, and you want to test whether these beta 1 regressors make some contribution, you would have to reshuffle the partitioning, and then you could compare this. But again, also for the distribution theory, this is all, it's fairly restricted to these nested models, which works fine as long as the regressors are independent. We will maybe in the summertime talk a little bit about independence of regressors, what that really means. If you have regressors that have a certain degree of collinearity, then it gets even more tricky. So if your models that you're comparing become even more similar, then this gets harder. But it's the classical theory, it works for certain cases. So the we might actually, like I said earlier, if we are looking in one-way ANOVA, we will, depending on how much time we have, compute the F statistic again like you did in undergrad statistic and show that the F statistic that we discussed today is actually the same thing. Because I assume that in undergrad statistics and ANOVA, you compute an F statistic based on within and between residual sum of squares and the ratio. And this is exactly, of course, the same F statistic as here. One just has to write everything up so that in the correct way, so that that works. Now, let's finally have a look at a simulation of the whole thing that will explain. So that's what you have in figure 12.2, simulation. So the example here is simple linear regression, like always. So our design matrix is this, and then our beta 1 has the interpretation of offset, and beta 2 has the interpretation of slope. And what I'm visualizing there in the first upper left panel is the independent variable, the dependent variable under the null hypothesis. So under the null hypothesis that beta 2 is 0. So if beta 2 is 0, we know what we expect in a simple linear regression case, namely that there is no slope, or the slope is 0. So we have a constant value of the dependent variable as a function of the independent variable. And what I then did was for these, I think it's 10 values here, obtain a lot of realizations, which are here shown as these little things. Of course, for each realization, this was from a multivariate Gaussian, one could now connect the dots, but then one wouldn't see anything anymore. And what I then plotted next was the residual errors, and specifically the reduction in the residual errors and there one actually sees, so then based on these samples, I did a histogram analysis of these, and there in the histogram one actually sees this thing with the chi-square distribution of this term. I mean, it looks fairly chi-square distributed with a low degrees of freedom to me. Don't know how it looks to you. The same thing for the only the residuals under the full model. Again, fairly focus on 0, where you could think of a chi-square distribution there. And then finally, and that's the most interesting thing, the distribution of the F statistic. So this is now F. So again, F being E1T E1 minus E12T E12 divided by P2 divided by E12T E12. I can say a lot of numbers, N minus P. And what I plot here is the, so I compute the F statistic for all of these simulations and compute the histogram. And I plot the density of the F distribution. Maybe I do that in red as on the figure. And what one sees is what one would expect, namely that the distribution, I feel like, whoa, Almost, no? That the histogram of the F statistic and the analytical result overlap. So this is now F. That's all. This is what one would expect under the null hypothesis. The more interesting thing is actually if the null hypothesis does not hold. So if H0 or if this is false, so let's just write beta 2 is not 0, and let's say beta 2 is actually positive, then of course you get the standard thing you expect for a simple linear regression, namely a slope x and y. And again, I took many samples of the simple linear regression from the multivariate Gaussian. And then you see that this reduction here now looks maybe a little bit normally distributed, but not really. I don't know what this should be. The epsilon 1, 2 actually still looks fairly focused on 0, which makes sense. So here you sometimes, of course, get quite large reductions, and this is maybe that's important. So here you get relatively large reductions in the variance, because in the residual variance, because of course E1E does not explain everything that's going on in the data, because of course in the data there's this linear trend. So the variance that you get here is sometimes quite large, and here you get a relatively small variance. So you get, for this difference, you get quite large values sometimes. And then if you plot the F distribution, again like above, for the correct degrees of freedom, and the F statistic that you compute, or that I computed, you see that this does not match. So you have the histogram and the analytical result, they don't correspond at all, or very good. Which is of course due to the fact that the F distribution describes the distribution of the F statistic under the null hypothesis. But here the null hypothesis is not true, so then there is no reason why the F distribution should describe the distribution of the F statistic. This is kind of a case where you would observe something here and then say, this because here you have much more probability than in the F distribution, so it's likely that you observe something here, and then you would say, okay, observing this is actually quite unlikely under the F distribution or something more extreme, so maybe the null hypothesis is not true. Yeah, so I find these. If you look at looking at the distribution of the T statistic, so empirically when you do simulations, looking at the distribution of the T or F statistics, if the null hypothesis is true, is semi-informative, or I mean it's informative because it shows that the analytical result and the empirical results from simulations can be the same. But really more interesting is if you look at the distribution of the statistic, if the null hypothesis is not true, and compare that to the null distribution, because then you see deviations. So that's the F statistics story as far as we push it in this course. There is much more one could do. like always, I hope to come back to the F-statistic to relate this idea of model comparison of nested models that we looked at today to your old story about the F-statistic in one-way ANOVA, because that's also informative. Good, yeah, so I'm done. Questions?
So if the slope was negative, then B2 could also be negative, right?
B2?
Before
Yeah.
we said that B2 has to be bigger than 0, and I wasn't sure why that was. That's something different because we're talking about the likelihood.
B2, that's true. I said it at one point. Here. It doesn't have to be. So I think, no, it doesn't really have to be. It just doesn't need to be. Just doesn't need to be 0. Yeah. So the thing was, I was thinking in terms of a positive contribution, but of course can also be a negative contribution, but it doesn't shouldn't be no contribution. Yep. Anything else? No. Good. So then from next week on, we will go over a lot of examples for general linear models, so that we finally cover everything that the GLM allows you to formulate, like t-test, 1 sample, 2 sample, ANOVA, and ANCOVA. Yeah? Good. Then let's stop here.